Hello everyone, I am Rhiddhi Subha Siddique. My metric number is A24CS4090. For this project, I will be evaluating CPU performance using PassMark PerformanceTest. The purpose of this benchmark is to evaluate the processor under two different workloads. Workload A focuses on the processor's general instruction execution performance, while workload B focuses on floating point computation and SIMD performance. Throughout the demonstration, I will explain how the benchmarks were executed, discuss the results obtained, and relate them to the computer organization and architecture concepts learned in class. Before running the benchmark, let me briefly introduce the test system. The benchmark was performed by the Lenovo laptop equipped with an AMD Ryzen 5 7430U processor with Radeon graphics. The processor has 6 cores and supports modern processor features. Now I will open PassMark PerformanceTest. PassMark is a benchmarking tool that measures different hardware components such as CPU, memory, storage, and graphics card. For this project, I only used the CPU benchmarks because they directly relate to the workload requirements specified in the assignment. For workload A, I used three CPU benchmarks test: integer math, floating point math, and sorting. Each benchmark stresses a different part of the processor. The integer math benchmark evaluates how efficiently the computer performs arithmetic and logical operations. These operations are handled mainly by the arithmetic logic unit, or ALU. The floating point benchmark measures the performance of the floating point unit, or FPU. Floating point calculations are more complex because they involve decimal values, exponent alignment, normalization, and rounding. These operations are widely used in scientific applications, engineering software, graphics rendering, and machine learning. The sorting benchmark evaluates how efficiently the processor organizes and manipulates data. Unlike the previous two benchmarks, sorting performance depends not only on computation but also on memory access, cache efficiency, comparisons, and branch predictions. As you have seen, I only used CPU mark and it is currently running. The integer benchmark achieved the highest throughput. This is expected because integer arithmetic requires fewer computational resources than floating point operations. The floating point benchmark recorded a lower throughput because floating point calculations are more computationally intensive and require a processor's floating point unit to perform additional processing. The sorting benchmark achieved the lowest throughput because sorting algorithms involve continuous comparison, memory access, cache lookups, and branch instructions. As a result, the processor spends more time managing data movement instead of performing pure arithmetic calculations. The assignment also required a MIPS calculation. PassMark reports million operations per second, or MOPS per second, rather than millions instructions per second, which is MIPS. Because PassMark does not report instructions per second directly, the integer math and floating point benchmark throughput values were used as an approximation of MIPS as specified in the report. Next is the CPI estimation. CPI stands for cycle per instruction, which represents the average number of clock cycles needed to execute one instruction. Since PassMark does not report instructions per second, an exact CPI cannot be calculated. Instead, I estimated the CPI using the processor's maximum boost frequency of 4.30 GHz together with the integer math throughput. The estimated CPI is approximately 0.15. I also analyzed IS structural bottlenecks. From the benchmark results, no major IS structural bottlenecks were observed. Although the floating point and the sorting benchmarks produce lower throughput than integer math, this does not describe a processor limitation. Instead, it reflects the higher computational complexity of those workloads. Overall, the benchmark shows that the processor maintains balanced performance across different instruction types. After evaluating the processor's general instruction performance, I proceeded with workload B, which focuses specifically on floating point computation and SIMD processing. This workload allows us to examine how efficiently the processor handles vectorized mathematical operations that are commonly used in multimedia applications, scientific computing, and artificial intelligence. For workload B, I reran the floating point benchmark together with the extended instructions benchmark, as you can see. The floating point result in this workload is slightly different from workload A because the benchmark was executed again as a separate workload. Small variations between benchmark runs are normal and may occur due to background processors, processor boost behavior, or system activity during testing. The floating point benchmark was then used to estimate the processor's floating point throughput. The estimated throughput is approximately 18.375 gigafloating point operation per second. In addition to floating point performance, I also analyzed the extended instructions benchmark. This benchmark evaluates SIMD performance. SIMD stands for single instruction multiple data. Instead of processing one value at a time, SIMD allows the processor to execute the same instruction on multiple processors of data simultaneously. Overall, the benchmark results indicate that the AMD Ryzen 5 7430U is a well-balanced processor capable of efficiently handling both general-purpose computing tasks and computationally intensive floating point workloads. With this, I will be concluding my presentation here. Thank you so much.